Graphical and numerical descriptions of bivariate data. Up to this point, we have looked at data description in the context of univariate data. That is, one variable observed on many different subjects, and we have a data set on one variable, and we want to describe that data set. Well, what if we observe more than one variable, in this case two variables, on the same subject or maybe on two different subjects, and we want to describe that kind of data? All right. Well, depending on the kinds of variables we have, there's different ways to summarize such data. So if we start off here first with two qualitative variables. Here's an example. Compliments of Dr. Robert Henderson, dealing with data from two qualitative variables. So what we have here is the two qualitative variables are the age category of a person and the severity of his or her skin disorder. So a patient comes in and say a nurse or a doctor classifies that person with a skin disorder as moderate, mildly severe, or severe. So the severity is one of the qualitative variables. The other qualitative variable is the age category. We've made it qualitative by forcing these categories here. Category 1, 2, 3, or 4. Okay, and so we have two qualitative variables here. We want to describe this sort of data, and here is what's called a contingency table. A contingency table, and it cross-tabulates according to these two variables. So if we look at the contingency table, this 15, the way we think of this number is that there's 15 patients that were in age category 1 and had moderate severity. And age category 2 had 32 in moderate severity, and so forth. There were 70 total patients with moderate severity, 78 with mild severity, 68 with severe as the designation for the severity of the skin disorder. So we have in this contingency table, the data is constructed in these 12 cells here, and then we have on this last column we have the row totals, and in the bottom row we have the column totals. Okay, and each of those, the row totals and the column totals, total up to the grand total of, there was 216 patients there. So this is called a contingency table, and it's kind of the rough form, the raw form of the data for this bivariate kind of data. We can graphically represent this in a couple of ways. One, in what's called a cluster bar graph, and also what's called a stacked bar graph. Okay, so a cluster bar graph is right here, and a stacked bar graph is right here. So let's take a look at these. The cluster bar graph, what it does is, according to age category 1, 2, 3, and 4, it clusters the other variable, in this case the skin severity. So we see that there's 15 moderate in age category 1, that there was 1 severe in age category 1, and we can move through the 4 age categories in that way, and we get a sense of the pattern of the data. The stacked bar graph gives us a similar picture, but we get a better sense of proportionally what's going on within each age category. So for example, in age category 1, there was one person that was severe, that green bar there. There was a few that were mildly severe, but most of them were moderate. As we move from age category 1 to age category 2, we can see that yes, there's more green, but the proportion of green is higher. In fact, proportionally, the amount of green is increasing as we move from left to right in the age category. Okay, so we see that sort of information there. So those are two quick graphs in describing two qualitative variables. What about one qualitative variable and one quantitative variable? Here's an example from the Journal of Chronic Diseases. So take a minute to read the problem set up here. Patients that undergo hemodialysis often experience severe anxiety, and so one way to deal with this is to try to relax the patients, and one technique that was done was to show patients a relaxation videotape. Okay, and the question in the study was, is the relaxation tape, does it reduce anxiety in some sense? And so we had to have a measure for anxiety as well, and there's a psychiatric measure that gives a score to that. Higher scores correspond to higher anxiety. Okay. Now, what we have here is one qualitative variable and one quantitative variable. So just to be clear, the qualitative variable is the type of video. The person was shown a relaxation tape, or the person was shown a neutral tape. Okay, and then the quantitative variable was the anxiety score. So on each person in this study, two variables were recorded: the type of video and the anxiety score. And this was all with the purpose to see, hey, does this relaxation videotape, does it reduce anxiety before dialysis? Now, so here's the raw data: relaxation tapes, neutral tapes, and their various scores. There's the data, and if you want to look at a side-by-side box plot, that's a common way to compare these two data sets. So there you can look at the side-by-side box plot of neutral tapes, relaxation tapes. This box plot was done in JUMP, and there's JUMP materials for you to figure out how to do this. But if you look at it, you get a sense that, hey, the overall scores for the relaxation tapes, there was more variability overall, but there was a big chunk of the relaxation tape subjects that had lower anxiety scores than those that watched the neutral tapes. Okay. Now later on we'll actually talk about formally comparing the data sets in a statistical inference sort of setting, but I wanted you to see the side-by-side box plot as a way to compare, in this case, two different data sets, but to look at one qualitative variable and one quantitative variable. Now, two quantitative variables. Okay, so here is some data to motivate this scenario. Some data from 13 sparrows, and it was their wing length and the age. So very young sparrows there. If you look at the age, and the wing lengths were changing pretty rapidly over that short time span. And so we're looking here at two quantitative variables. The age is one quantitative variable and wing length is the other. Graphically, usually this is represented with a scatter plot. Okay. And so we have, for this kind of bivariate data, that's paired data, we look at it graphically. Okay, so when you look at wing length versus days or age there appears to be a positive relationship. That is, as wing length increases, the age of the bird is going up, and that seems to be very natural. But more than that, we see a nice linear relationship between the two. Okay, and there's a particular way to measure that linear relationship. And a numerical measure that does that for us is called the correlation coefficient. In particular, it examines the strength and the direction of not just any relationship, but the linear relationship between two quantitative variables. Again, that's called the correlation coefficient. Here's the formula. R is the designation for it. We think of this usually as a sample correlation. There is such a thing as a population correlation, which we might address later in the semester. But the numerator here out front has 1 over n minus 1 times the sum of the deviation in x times the deviation in y. Then it divides all of that by the standard deviation of x times the standard deviation of y. Okay, so we've got to be comfortable with computing the standard deviation and dealing with these sums in order to compute this correlation coefficient. Now, a few properties of the correlation coefficient are described here. So one thing, take a look at this picture. This is from Wikipedia. It's got various scatter plots and various their respective correlation coefficients. And over here we have a scatter plot. The upper left corner, we have a scatter plot where the data falls perfectly on a line, and the correlation coefficient is 1. Now the data is increasing, so we have a positive 1 correlation. On the other hand, if the data is decreasing over here at the far right corner, we have the data is decreasing, but it's decreasing on a perfect line. The data lies on a perfect line there, and so the correlation there is -1. Okay. Now in between these two, we have varying values of the correlation. So here the correlation is 0.8. The data seems to be, somewhat tightly packed around a line that's positively increasing. Here the correlation is 0.4. It's still positively increasing, but the strength of that linear relationship doesn't seem to be is not what it was when we were at 0.8. And when the correlation is 0, it's like a random shotgun scatter. When the correlation is -0.4, we have the data, the scatter plot is, again, it's decreasing from left to right, and it's not tightly packed around a line. When the correlation is -0.8, the scatter plot has a decreasing trend there, and the data seems to be somewhat tightly packed around the line. Okay, the second row of this table is different scatter plots. The correlation coefficient in all of them is 1. Well, really, except this one here, the correlation coefficient is 0, and this middle one here. But the point of that picture is that the correlation does not tell us the value of the slope of the line. It just tells us how tightly packed the data is around the line and the direction of that relationship. Okay, the bottom row here is a bunch of scatter plots where the correlation is 0, but the patterns reflected in the scatter plot do not suggest that there's no relationship, rather that the relationship is not linear. So for example, when you look at, say, this plot here, this correlation is 0, but you would it suggests that the relationship is parabolic. So maybe a quadratic function would fit that relationship there. Here the relationship is circular, okay, but still the correlation coefficient is 0. So be aware of this sort of thing. In general, the correlation coefficient describes the strength and direction of the linear relationship. Okay, so let me fill in the blanks here. If all of the points lie perfectly on the trend line, then R is exactly -1 or 1. So values close to -1 and 1 reflect a strong linear relationship, while values close to 0 reflect little or no linear relationship. Now that doesn't mean they're not related, it just means that they're not linearly related. Okay. Alright, so moving on here, if we are dealing with this sparrow data, I can use Excel, which is a powerful thing, even to do some basic statistical analyses. We can use Excel. Here's the original data, the age and the wing length. And within Excel, I got it to compute for me the square deviation in the y's. So this right here is yi minus y bar squared. This is the square deviation in the x's. Xi minus x bar squared. And then this right here is xi minus x bar times yi minus y bar. Okay, so you could do these computations by hand to verify these results. But what do I need to compute R? Remember the correlation coefficient, the formula looks like this. It's 1 over n minus 1 times the sum of xi minus x bar times yi minus y bar, all divided by the standard deviation of x times the standard deviation of y. Okay, so let's start with the numerator here. N, if you count the data points, there's 13 data points. The sum here, this is the sum of what I say the product of the deviations. So it's the sum of the product of the deviations. And this last column here gives me that information. And so this 14.10, how did we get that number? Well, it was 3 minus the mean. Well, let's back up. It was 1.4, that first x value, minus the mean of the x's, times 3 minus the mean of the y's. And that gives the 14.107 there. Adding all of those up, I get 70.8. So this quantity here is 70.8. Now what else I need is I need my standard deviation of x and standard deviation of y. Okay, so I'm actually going to work through the variance of x first. The variance of x is going to be, let's see, I'm going to take the square deviations in x, add them up. That's this value here. It's going to be 19.6, we'll say 19.66 divided by 13 minus 1. That's my formula for the variance of a data set. Do the arithmetic there and you get 1.63. The standard deviation of y is going to be the sum of the square deviations in y, which is 262, divided by 13 minus 1. You do the arithmetic, you get 21.83. So those are my sample variances. So coming back to the sample correlation coefficient, if I plug in there, I have 1 over 13 minus 1 times 70.8 divided by s sub x. So I got to take the square root. I need to take the square root of 1.63 and the square root of 21.83. That's the standard deviation of y. Do the arithmetic here in the numerator. You get 5.9. In the denominator, you get 5.965, and that turns out to be 0.989. Okay, so that value is very close to 1, and it tells us that age and wing length are very highly positively correlated for this data set. And we're not too surprised if we look at the scatter plot of the original data. If we were to fit a line through the data, the data fits is pretty tight around that line. And so we would expect a correlation to be positive because that relationship is positive, but also to be close to 1 because that data is tightly packed around that line. Okay, moving along here. One important caveat or warning is that, again, the correlation coefficient is a measure of the linear relationship. Other kinds of relationships might need different kinds of measures. Here's these. In this picture here, I have 4 scatter plots. They all have the same correlation of 0.81. The upper left scatter plot seems to be linear just looking at the scatter plot, and the line fits it pretty well. It has a correlation of 0.81. The upper right scatter plot, really to call that a line or to think that follows a linear relationship would not be the best choice. That data appears to follow some sort of quadratic relationship. So to use the correlation coefficient to measure the strength of the linear relationship really isn't appropriate there. The data on the bottom left, all the data is in a perfect line except one point is off a little bit. That gives the correlation of 0.81. Not quite. Let's see. So bottom right here is we have again a correlation of 0.81. We have data stacked on top of each other when x is equal to 8. A bunch of data stacked there, and then one single data point off upper right here and you fit the line through it. The correlation coefficient is still 0.81. And so really when we think of what kind of data is it appropriate to use the correlation as a measure of the strength of the linear relationship, it's really with this kind of data. You know, this one maybe, and this one a little bit, but definitely not this one here. Okay. Another thing with the correlation coefficient that I want you to be aware of is that a high correlation is commonly mistaken for a cause and effect relationship. Okay. And that's the warning here. That's a common mistake. An example here is that several epidemiological studies show that a high-fat diet is found to be a risk factor for breast and colon cancer. Now, it turns out from a study like that, we can only say that a high-fat diet and cancer have a strong association, and not that a high-fat diet causes cancer. It could be other factors involved, or there are other factors involved in a person developing breast or colon cancer. Okay, so correlation coefficient, a measure of the linear relationship between two quantitative variables. But overall, this video deals with describing data from bivariate data.